So I'll make an announcement about the final later today. So but I think I have decided to make it an open book, open Mathematica, open everything, and it will be for about 5 hours. Yeah, so like you'll have 5 hours, 5-hour window to submit your papers within a 20. Yes. So you need to do work on the final within 5 hours, and then you will be given a 24-hour window. Yeah, so we'll copy it and let me write it down. So today we'll finish with the material of the course, and tomorrow and on so tomorrow will be like a free day. It will be like an office hours day. If you want to have ask a question, we can. I mean, we can meet during the lecture as well, and as well as in office hours. And on Thursday there will be some review. So we'll go over some problems from the Math 53 worksheet. Is it 5 hours long for the test? Expected to take about 4 hours with an hour of leeway. Yeah, that's right. So basically, I'm thinking making problem a little bit more interesting, given the fact that you can use resources. You can, look up some facts, formulae, and even check your answers in Mathematica. But yeah, so make problems slightly more interesting this way. Yeah, so like, so typically a final is 3 hours, and then it will be a bit longer. But like, I mean, it's not like, it will be that much longer. So I just wanted to minimize people's stress because last time with the midterm, there were quite a bit of, so maybe like 10 people or so who claimed to have had time constraint problems. I don't think that we want that. Right, so I am. If you go to the web page that I put it on my Berkeley page. I can give you the link again. So I'm collecting links there. So if you have, so now I think all lecture videos are there. Yeah. So if you go here, we have all lecture videos for now, and then included at the bottom the preparation materials. So there's a link to Math 53 worksheet and the list of exams and midterms at this fraternity, the tau beta pi. Yeah, so I think the closest professor to whose exams I'm sort of, if you look at the midterms and at the finals, so if you look at the Edward Frankel's exams there, I think those will most closely represent my final. Yeah, so, but of course, because we have a different format, we'll add a bit more structure to it. There'll be more problems. So I slowly start moving videos from Zoom to YouTube because they have expiration dates. So the last week lectures are already on YouTube. Yeah, so I think I plan to put all the lectures to YouTube. And then yes, correct. Final will be open everything. Yeah. So I think the only thing that I ask you not to do is to talk to each other. So it has to be done individually, and you have to, yeah. But otherwise, you can use stuff. On tau beta pi, I haven't been able to access the other exams because site has been having downtime for weeks now. Interesting. I think I used it later, like before for. Okay. Okay, so it works for Alex. And now it works. Okay. Yeah, maybe it was down for like some time ago, but now it should be fine. Yeah, sort of. Well, let me try now. So, because I was able to get in. Yeah, I see the links of others. And then you can find even more material if you just Google, Math 53 Berkeley, and then there'll be more classes that will pop up. And they have similar structures, like similar web pages as mine, and with even more material there. Yeah. Yes, I also post solutions of midterms once the TA send them back to me. So, Any other questions? Okay. Yeah. So you might have, if you have any problems, yeah. Good. So last time we talked about Flux. Flux is, let's remind ourselves what it is. Oops. I see what's going on. So when we have a parametric surface, right, which is given by a vector function, there's a question. Maybe because I had VPN. Yeah, maybe because of that. Yeah. So I don't think that. I mean, this website is just it's hosted somewhere on campus, right, or one of those fraternities, or shouldn't be any problem. Not that it's in China or somewhere. Yeah. So so we have a surface with which is parameterized by a vector function R of u and v. So which means that there are three equations, three parametric equations. X equals x of uv, y equals y of uv, and z equals z of uv. And then there's a vector field f, which is defined, let's say, everywhere in R3. And because of that, in particular, it's also defined on the surface S. And then we can ask ourselves, in which direction is this vector field, where does it point at the surface, right? So those we can only sort of look at the direction of the vector field and its magnitude of the vectors at the surface, right? And then if we dot the vector field with a unit normal vector, we can get a scalar function which we can integrate over the surface. So, and then if you work out the explicit parameterization here, so if parameters u and v belong to some set D, then the flux, which is by definition is the integral of this vector field over the surface, is equal to, well, to triple product, right, of vector field on at the surface, and then tangent vectors in u direction and tangent vectors in v direction. Well, you can write it as f dot ru cross rv, because this that's how the normal vector is computed. And we ended last lecture with a calculation of the flux of the Euler vector field through the sphere. Yeah. Okay. Any questions? Let's see if they have any more space here in the book, in the page. Okay. Or we should start the new page. Right. And then, so now let's, so we'll talk about the divergence theorem now. Oh, the page loads. So the idea behind the divergence theorem is analogous to the idea behind this Green's formula. So let me remind you, Green's formula well, I'll write you two ways to do it. One using differential forms and one using the more explicit notation. So more explicitly, so if we have a connected set, let's restrict it to the connected set, simply connected set, right? And then set D with boundary del D, and then there's a vector field F with components P and Q. Right. Then we know that the integral over D of the following combination Qx minus Py dx dy is equal to the closed line integral or contour integral of the boundary of the vector field F. Right. And the right-hand side can be understood as, is the integral of f dot dr, right? Where, well, dr has components, it's differential, or it has components dx dy, right? And f is the vector field. And also in terms of differential forms, we know that we can write it like this: the integral of d of the round differential of omega is equal to integral over the boundary of d of omega. So here omega is a differential one form, and so that is omega. Okay, so in this formulation, it's also known as Stokes formula. Now, if you wish, this formula allows you to interpolate between a two-dimensional integral and one-dimensional integral. Now, the divergence theorem, or another name for this, is due to two mathematicians. One of them, the first guy's name was Ostrogradski, Polish mathematician, and Gauss. Is to write the analog of this formula for which connects a two-dimensional integral and a three-dimensional integral, right? And that's what it says. And so the divergence theorem, Ostrogradski-Gauss, or the divergence theorem. Although I mean it's not quite that, because before I go there, let me make one more comment. Yeah, sorry. So there's a Stokes formula here, and then so remember we have two formulas. So there was this formula, and then we also had a formula where we sort of had an analog of the flux, right? Of the vector field that goes through the surface. So say you have, vector field that goes like that. Right. And then there was an analog formula of the flux, right? So it was like this, that the integral of the divergence of the vector field F over D was equal to contour integral over the boundary of F dot n ds, right? Where n was the normal vector to every point. N was the normal vector in the boundary, but it's a vector field as well, right? It's a collection of normal vectors to every point on the boundary. So you would calculate the dot product, and then you would and then you calculate this formula. So Ostrogradski-Gauss theorem is a generalization of that formula, right? To 3 dimensions. So that was sort of 2D, 1D formula, and now we can write the 3D 2D formula, which says the following: that if you have now let's say you have a volume, have a solid, some 3-dimensional solid inside, let's put, as was taken, B, right? B for bulk, right? So there's a solid B, and then there's a boundary dB, right? Well, I'm not going to draw it all, it's kind of the surface, the boundary of this thing, dB, which is 2-dimensional. So the theorem says that the 3-dimensional integral, and then if there's a vector field that also is everywhere, there's a vector field in R3, which does something like this. Then the triple integral of the divergence of f dx, dy, dz over d is equal to, sometimes it's not like this, it's a double integral over the closed surface, right? So whenever it's closed, sometimes we encircle the integral. So in LaTeX, it's O E int, right? So there's O int and then there's O E int. There is no O triple I int. But yeah, integral of dB of f d ds, where the right hand side is the flux, and this is the integral of the divergence, integral of the divergence of f. So that's the divergence theorem. Right. So now, okay, let's talk about the proof. Practice final being released soon. Well, I mean, practice finals are at this exams archive. So yeah, so I'm working on the final right now. So it's something that I mean, so like I said, the level of difficulty should be the same as before. So if you look at the exams archives, you'll get a good representation of what's going on. Yeah, that's right. That's the it's one of the lists of those steps. Yeah, sure. And then so if Rohan, if you're just joining us, so I have decided to make a final open book, open Google essentially, open Mathematica, but without, you're not allowed to talk to your friends. So you have to do it by yourself. And there will be 5 hours grand total for everything to solve the problems, write them down, and upload the solutions to Gradescope. Okay. So how shall we prove it? So do you remember the proof of what was the proof of the 2-dimensional case, right? So here it's the same, it's the same idea. So we have to, if you have this solid B, right, we can cut it into, so all in all, it suffices to prove it for a parallelepiped. And so if you have a right? So if you prove it for the parallelepiped, then we can, well, every three-dimensional shape can be sort of cut into little parallelepipeds, right? So that's how we construct the Riemann integral, also over surface or over the volume. We would, remember we discussed the 3D integral. So 3D integral is like you take your solid, then you would tessellate it into little cubes, and then multiply the value of the function inside each cube by the volume of those cubes, and then take the sum. And then in the limit, if the limit exists, you'll get the value of the integral. So if we have, if we have the bunch of parallelepipeds, if you prove the theorem for one parallelepiped, then it will be sufficient. We can deduce from here that we can prove it for any shape. So there's sort of maybe one comment here due is that if there's a normal vector, so it goes here from this face, right? So when you attach the next adjacent parallelepiped to it, right? So there's another parallelepiped that goes here. So say it's one of those parallelepipeds that appear in a tessellation of the thing. So let's call it maybe N and I, right? And then, so this is the ith parallelepiped, and then there's the next one. There's I plus first parallelepiped over here. Right, so it's I plus first, and then we have a vector Ni plus 1. So if the two guys, if they share the same face, like this face over here, then the normal vectors from the two adjacent parallelepipeds will be opposite to each other. And therefore, when we add the flux, when we add the fluxes from these two adjacent parallelepipeds, the contribution from common face will cancel, right? So the only thing which will not cancel is the contributions from those faces which do not have adjacent faces. So see, if this face does not have an adjacent face, then this contribution will survive, this contribution will survive, this contribution will survive. So I'm drawing normal vectors here, and then say vector field F has, goes somehow like this. Right. So yes, it suffices to prove the theorem for a parallelepiped. Yeah. So let's start off with the divergence, or with the right hand side, right? So the flux, the flux contribution, right? What is it? So remember, it's the integral. We take the dot of f with a unit normal vector, right, and then integrate it over the area. And let's say vector field F is given by three components. So P, Q, and R. So then we have the following thing, right? So we have the integral of P dA, right, plus integral of Q. Well, I mean, it's actually, yeah, so hold on. Be a bit more careful. The dot product will still stay, right? So it's basically I dot basis factor I dot N. So P is the X component, right? So plus double integral q dA, right? J dot n and plus r k dot n dA. And now we need to look at each of those terms individually and then re-express them as an integral of some three-dimensional volume. Right, so here, for example, so the first term here, the integral of p of the x component, right, it will only capture the projections, right? It only captures projections of the vector field that we integrate sort of. It only captured the x-axis projections of the vector field, right? So we can rewrite this term as so in other words, if you look at the face, right, so then if this parallel, I'm just going to draw another picture of the parallelepiped, maybe a bit smaller one. So this is x, y, and z. So when we look at the projection in x-axis, we only capture the so in other words, x projection, we only have a non-zero flux through this face and through that face, right? So that's the p. It's the flux of p. So flux of p will only have non-zero. This integral will only have non-zero contributions for these two faces, right? In all the other faces, the corresponding vector will be parallel to those faces, and it will not give any contributions. So therefore, if you think of this, this this segment A, so well, that we don't really need it, right? So if you only look at this. So right, so and this is the face, this is the front face and the back face in the x direction. So we can rewrite this integral as a volume integral of the derivative of p in x direction, d volume, right? Simply because it's a total derivative, right? And then if you get the if you do the integral, you'll get you'll get two contributions. One of them will be flux through this face, and the other will be flux through that face. And because of the orientation of the normal vectors, you should one will go with plus sign, and the other will go with the minus sign. All right. So here the normal vector points this way, and there the normal vector points that way. Okay. And similarly, we can rewrite this guy as a triple integral dB or dq over dy, and this integral, this would be triple integral over dr over dz dv. Okay. So yeah, so that's more or less the proof, right? So if you sum them together, you get on the nose the volume integral of the divergence of f dx dy dz. Right, so which completes the proof. I'm gonna move it up a bit so you can see the whole derivation. So now, let's look at the example now. Remember, last time we struggled so much with the calculation, and even I made the mistake again. So I think I made this mistake like 3 or 4 times, right? But because in my calculations, in a notation that I know from my childhood, right? So phi always a polar angle, and theta is the azimuthal angle. So, and in the book, it's the opposite. So maybe I should have just ignored the book, as I do most of the time, and do it in my own way. But anyhow, so yeah, like you would wake me up in the middle of the night and write the formula for spherical coordinates. I would write them in my way. But anyway, so yeah, so basically this is what the formula allows. So typically fluxes are harder to calculate, right? Because you need to worry about the directions of the vectors, right? And you have to calculate the dot product everywhere. It may not be as easy. And sometimes the divergence f is an easy task, is an easy calculate the left-hand side in the formula. It's easier. So let's solve the problem from last class from the very end using the Ostrogradski-Gauss theorem. Okay, so example. So we take vector field f, which is well, a vector field x, y, and z, right? So and then we want to calculate the flux through a sphere, right? So through a sphere of radius r of this vector field. Right, so sphere of radius r has equation x squared plus y squared plus z squared is equal to r squared. Right. So according to the Ostrogradski-Gauss theorem or the divergence theorem, that flux, let's call it phi, big phi, right? So it's often denoted the flux. So this big phi will be equal to the triple integral over the volume of the sphere, this 3-dimensional ball of radius r, of the divergence of f. And what is divergence of f? Following, this should be div f dv. What's the divergence of f equal to? Yeah, but what is the answer? F has components x, y, and z. It's a number, which is equal to what? So this means that it's a vector with components xi plus yj plus zk. What does divergence do? Yep, of course. It's 3, right? So it's dx over dx plus dy over dy plus dz over dz. Right, so I remind you the formula for divergence is it's fx plus fy plus fz. Okay. And that's it. So just three times the volume. So it's 4 pi. That's it. R cube, yeah, but okay. So if you want R, the last example was with the unit radius. So yeah. So remember last time. So although it appeared differently in the calculation, excuse me, that we had the contributions from 3 pieces, right? And each of them was equal to 2/3. And I told you that each direction, x, y, and z, will give you 2/3. Well, here it's actually trivial, right? So in this other units, each direction will give you 1. So it's like 3 dV, so 3 comes because, you know, this is equal to 1, this is equal to 1, this is equal to 1, right? And the, yeah, so 1 plus 1 plus 1 equals 3, so that's the answer. See, it's much, much quicker. Okay. And now let's do the formula with the point charge, right? So the yeah, can only do this in the case of closed surface integration. Yeah, that is correct. So the surface must be closed. Yeah. Otherwise, if it's not closed, you'll have a boundary contribution. So say you will get some, you know, and you'll get, you know, like a shape like with an opening, like with a hole here. Then you'll pick up some boundary contributions from here, and the formula will look different. It will not be particularly useful in that case. Okay, and so now let's talk about. So we'll look at this example with a point charge. So you have a electric charge Q, right? So there's a electric field lines which go in all directions radially, right? So it's equal to Q R over R cube, right? And then we want to calculate the so we want to calculate the do I have 4 pi? Yeah, okay. Well, let's do it here. So so remember last time when we calculated the divergence, so the divergence of E was equal to 0 everywhere except the origin, right? So it's equal to 0 when R is not equal to 0, and it was equal to, well, infinity. So it's an imprecise statement when R is equal to 0. So it was divergent when R is equal to 0, and then I told you that this should be understood up to some coefficient as a delta function, the 3-dimensional delta function at R equals to 0. And so this is a function whose integral over the volume over R3 is equal to 1. So it's a, you should think of it, you can kind of think of it as a limiting shape of a distribution, which is whose support is around the origin, and then you make this distribution thinner and thinner by keeping the integral the same. Right? Like say in 2 dimensions, you would have, you know, you would have this Gaussian bell-shaped distribution, which we talked about, and you can make it thinner, but then those peaks will become higher, right? So that integral area under each of them will be equal to 1. So now you push it all the way down, and then in the limit you'll get a function which is 0 everywhere except the origin, where it's formally equal to infinity, and that's what the Dirac delta function is. So the divergence of U will be Dirac delta function in this case. So therefore, we expect that the integral integral of the divergence of E will be equal to 4 pi Q, because, well, yeah, will be equal to 4 pi Q over the, so if you take a sphere of any radius, right? Radius is not really important, right? Because so as long as radius is a positive number, right? So since this is equal to 0 everywhere, so the only point in space which you worry about is the origin. So as long as the sphere encloses this point, we are fine. Right? So let's check that this is true using the divergence theorem. So claim, right? So that the divergence of this vector field is equal to 4 pi q. So let's verify it in terms of using the flux, right? So let's calculate the flux of the electric field. It's called big phi, equal to integral through this sphere. En dA, right? And the what is the normal vector to a sphere, right? We can take a vector. So normal vector will be equal to, we talked about this when we did Kepler laws, right? It's the radius vector r divided by its length. And so therefore it will be equal to q over r cubed times r dot r over r dA. Okay, so that's equal to integral of the sphere q over r squared dA. Now it's a scalar function, right? So r dot r is equal to r squared, and then things cancel, and we can switch to so we can switch to spherical coordinates, right? So here radius is fixed. And actually, it's even so if sphere has a radius big R, because we know that it's a surface integral, we can replace it by big R, which is a constant, right? So that's capital R is the radius of that sphere. So we don't even have to do any calculation because this is a constant, and then we have integral of 1 over dA over S2, which is equal to the area of the sphere, which is 4 pi r squared. Right? So the answer is equal to 4 pi q. And so therefore, this claim is correct. Yeah. So notice here that it was up to us to pick the surface, the sphere. If you picked any other surface, the answer would still be the same, right? Because when you calculate the normal projection here, this E dot n, it's as if you only worried about kind of the part of the surface which is perpendicular to the normal vector. The rest is not important. Questions? And I have, I think, one more little story to tell you. It's about orientation, orientable surfaces. And then it will be another illustration of why we need differential forms in this wedge product. And so we'll do it by doing two examples. So example 1, we'll take a strip. long strip of paper, and then we identify these two ends like this. So it will make a, this will make a cylinder. Okay, and that's the first thing. And then the second thing we will do, we'll take this same long strip of paper and we'll identify the ends with a twist. Right, so we twist it and then we glue it. So then it would look something like this. Like this twisted ribbon. And so, well, this is called the cylinder. And probably you know this is called the Möbius strip. So it's an umlaut here. Yeah, so you twisted it. So both can be obtained by identifying the opposite ends of the of a rectangle. So this is so-called identification topology, right? So when you identify different components of the boundary in a different way. And just sort of before I go to the orientation, you probably know what happens next, right? So if in addition you identify these two boundaries like this, which shape, which surface will we get? So it will be the same as identifying these guys. We could have glued them together up like this. We'll draw this in Mathematica. What kind of surface is that? Didn't get a graph thing above. Which graph? So we take a rectangle, then we identify opposite. Yeah, torus. That's right. So if you identify them here, you'll get a torus, right? So it will be doubly periodic, right? So if you move, say here, you get to the boundary, you will reemerge on the other end. That's what this identification topology stands for. Right? And then if you go up, you'll reemerge over here. So say this green circle, if it's long, so the blue line will go this way, and then the red will go that way. Yeah, so if you do both of the identifications, you will get the torus. And then you can ask yourself, what happens in this case if you identify sides like this? What you'll get in the end? So you need to identify. It's actually quite tricky, right? So, like they look like so they interlace, right? The boundaries, because of the twist, they switch, and then you would try to identify them. As you may imagine, it's not possible to do in 3 dimensions. Like it's impossible to write. Although torus is easy to draw, you know, it's a donut, right? This Dunkin' Donut thing, the boundary of that, which you can draw in 2 dimensions. You cannot do that with an identified Möbius strip, right? So you need to go a bit 4 dimensions. But anyhow, if you do that, you'll get something which is called Klein bottle. It's not really a bottle. It's, you know, whatever it is. It's like the so you should think of it as taking a cylinder like this and then glue it on top of this Möbius strip. Yeah, that's right. So Amok knows that, right? So and you'll get a surface which is if you try to draw it in 3 dimensions, it will have self-intersections. But nevertheless, as a topological space, it's a 2-dimensional space, right? Because locally, it looks like a little. If you take a little patch, little open neighborhood, it will still be two-dimensional. Okay, so since we are looking at these examples, let me go one step further. So to exhaust all the possibilities, you should consider this. You should consider taking a strip and then identifying both opposite ends with a twist. All right. Does anybody know what that is? Again, so obviously you cannot draw it with a in 3 dimensions, right? It will be something with self intersections. So this is known as a real projective plane. Or RP2. You can imagine it this way, by taking a half sphere, a hemisphere like this. So it's a hemisphere with south pole, so it has a boundary. And now you glue this boundary with a Möbius strip. So see, the trick with the Möbius strip is that it has only one boundary. Like although, so cylinder has 2 components of the boundary, right? There's a circle, this upper circle, and then there's a lower circle. So it has 2 components of the boundary. This guy has 1. Let's see, right? So I'm gonna put my I'll start from here, and then I'll just go along the boundary, right? So I go. Just gonna make sure that there's no delay in when I'm drawing, right? So do you see my thing? Right, so then you go, then you dive under, you keep going, and you keep going, and you keep going, and you come back again to the same point. Right, so the boundary of the Möbius strip is just a single circle, although it's sort of kind of twisted inside, right? It's a, let's call this Möbius strip M. So a boundary of M is just a single circle. Whereas the boundary of the cylinder, let's call it C, is the union of 2 circles. Yeah. So that's pretty cool. And now imagine this Möbius strip and glue it, since its boundary is a circle, you can identify this circle with the boundary of the hemisphere, right? So if you glue them together in this identification topology, you'll get RP2. Yeah. So we think of RP2 as the hemisphere whose boundary is glued with the Möbius strip. So it's like as if you think equivalently, you can say that you just take opposite points and identify them, right? So you would identify this point with this point with that point, that point with that point, and so on. Yeah. So this will be the real projective plane. So the reason why it's called real projective plane, you can put it this way: you take a sphere, right, in 3 dimensions, and you would draw all rays that pass through the origin, right? And then you consider those rays as points in this new space, right? So in topology, points in space can be anything. They can be lines, they can be subsets. So kind of you make new spaces like this by sort of declaring what those points are, right? So in topological, yeah, and then so in this new space, those points, but the actual points without quotes, I mean, they are points with quotes for in the normal kind of understanding, but in topology, it's a new space with a point. So a line here is a point, so line in R3 passing through the origin. Through 0 is a point in RP2. Actually, it's RP3, I think. Yes, it's RP3, excuse me. So it's a plane, but it's projective in 3 dimensions, right? So it's real projective in 3 dimensions. So you can see here that it cuts through the sphere into diameter points, right? Sort of the two opposite points. And it suffices just to look at only one of them, right? So since you have to identify only one line, it suffices only to look at one of them. So we cut the sphere in half. That's how we get a hemisphere. And now we need to identify the points on the boundary, because again, according to our rule, these 2 points should be identified. And because we're doing this in the diameter kind of sense, it's equivalent to taking a Möbius strip and gluing it onto that boundary. Yeah. So these are all 3 things you can do with it. So these are the identification topologies of a rectangle. As you see, the story is quite rich. Anyhow, I hope it was a well advertisement of Math 142, Intro to Algebraic Topology. So yeah, if you consider taking it, I highly recommend. Now let's talk about orientation. So you may sense, so which of those spaces that we listed so far are, without knowing the definition, which of them you think are orientable and which of them are not orientable? So if you think of, so we mentioned orientation quite a bit, right? Like, what does your gut feeling tell you? What would they look like? Like if it's an orientation. So, so think of orientation is basically when you always can say where's left, where's right, right? And then you can continuously apply this idea throughout the space. So, for example, do you think that a cylinder is orientable? Cylinder is not orientable. Why not? So okay, so yes, it has it's orientable, right? So there are, yeah. So there's an inner surface and then there's outer surface. That's right, and then you can sort of and then you can switch between one another by changing the role of vectors, right? So say, okay, let's maybe draw a little bit bigger cylinder. So say you have a cylinder here, and then say this is x direction, this is y direction, and then we can calculate the normal vector just by taking the cross product of those derivatives, right? Rx cross Ry, which will be like this, right? And then sort of the orientation is a global property, right? So which means that it has, you have to move. So the idea is that once you, so think of orientation as basically literally like this, saying where is left, where is right, right? So we have given the coordinate description here. So x, say x direction will be horizontal. So as you go at the same altitude level of the cylinder, you are moving in the x direction, and then y is moving up or down. Okay, and then this notion of where is up, where is down will stay if you move around the cylinder, right? So if you go around and come back again, you'll still get the same vectors, right? X and Y vectors will still be the same, and then the normal vector, you can sort of parallel transport it around like that. It will come back to the same vector. Now, I think what Hannah was referring to, the 2 surfaces, that if you decide to swap them, if you say swap x and y, then your normal vector, which you calculated by this formula, will point inwards, right? That's also fine. Yeah, so if you decide to do so, it will point inwards, and then if you go around, you'll come back again, it will still point inwards. So we call such surfaces, when spaces in general, orientable. So cylinder is orientable, torus is orientable, right? You can check that the same happens with torus. There's no problem. But the problem starts with this twists, right? So if you have a Möbius strip, then let's see what happens. So say, so you know, it suffices only to look at the position of the normal vector, right? Because say we have normal vector here, right? And then you can imagine what happens after you do the twist and you come back, right? So Okay, let me try to draw it, although I don't promise to make it good. But you can see here, as you go through this twist, you see that the direction of the normal vector flips, right? And then it will go like this, like that, like that. So once you travel on the inner side, it points inwards. And then when you come back again to the same point, after you've completed the circle, the normal vector points now in the opposite direction, which is not good, right? So, which means that there is a problem, which means that, well, it has weird, strange global properties, right? So that the you made a loop, you went around once, and it flipped your normal vector. Sort of normal vector in the sense that you define here, right? As you pick your coordinate frame, so x goes this way, y goes that way. So it turns out that this choice was inconsistent with the global topology of the surface. And so the Klein bottle is not orientable. Right? And so does the real projective plane, right? RP3 is not orientable either. Now, yeah. So basically, there's a bunch of interesting spaces with interesting topology, which are not orientable. Now, a little bit more, what does it mean in terms of calculations, right? So say you want to integrate something. So you want to integrate something of the Möbius strip, and that there might be a problem. So see, when you do integrals, so Möbius strip is a two-dimensional manifold. So you want to integrate over M some function, right? And then you would need to write dx wedge dy, right? But what is dx wedge dy? Well, so remember, it was related to the choice of the coordinate system, right? So when you have, if you pick your coordinate system like this, so you have the preferred choice of how to write the volume form, right? So here it's the area form. So dA was equal to dx wedge dy, and then remember it was equal to negative dy wedge dx. Okay, so if you make a choice of your coordinate frame and then you write down the area form dx wedge dy, so what happens that if you go around the Möbius strip once, your normal vector flips direction, and as we discussed, it's equivalent to switching x and y. So it's equivalent to replacing x with y and y with x. As we know, that results with the minus sign, which means that if everything is consistent, that must be equal to negative dy dx, right? And it's because it's essentially the same integral. The only consistent choice for this answer is to put it to be equal to 0. Right. So if the space is not, if the manifold is not orientable, then you cannot integrate. Then in other words, it does not have a well-defined form of top degree. Right. So it's a two-dimensional manifold, which therefore it does not have dx dy form. It's not globally defined. It is defined locally, but it is not defined globally. Yeah. And if it's not defined globally, you cannot integrate. So I mean, essentially, you can say that the integral is equal to 0. It's the only consistent value. Okay. So yeah, so that's that was the little algebraic topology did work. Well, I think that completes the course. So we have covered all the material necessary. So we don't need to learn more. I think it was already quite overwhelming for some of you, given we had 8 weeks. So yeah, so we have a final on Friday. So today I'll send the directions, and so we'll have a review session. So tomorrow we'll have office hours at 2, and we'll have another review session on Thursday. So if you have any questions, just let me know. You can send me email at any time. Yeah. Okay. So we have the strongest devoted crowd. I think there are 15 participants. 2 of them are myself. So we have a lucky 13 who went to all lectures. Yeah. So thank you guys for coming. So I know that some of the instructors decided not to do synchronous lectures at all. So they just pre-recorded in topic by topic, like Mike Hutchins, right? So he has this sets of videos, and I think that's what he does when he teaches Math 53. Yeah. So, but I think also like part of the interaction like this is also useful. Like, although to be fair, I have no proof to say that you guys are real, right? So. Yeah, sure. Yeah, so like as you probably heard this story that we all live in a simulation. So in this area, in the area of Zoom, era of Zoom, it's even more. This question is even more, more urgent. Okay, any more questions? Okay, great. So then I think we should adjourn today, and then we'll continue. Yes, office hours tomorrow too. Yeah, like there's no. I mean, there will be a review on Thursday, but I mean, just since I mean, not too many people show up anyways, I think we just do the review. So like we'll take a break tomorrow, and then we'll do another review on Thursday. So please bring your questions. Yeah, and then otherwise tomorrow there will be office hours at 2. Great, thanks guys. I'll see you later. Bye.